My name is Scott Young, and I will be your entertainment for the next little while. I'd like to begin from a good place. We're here at the Manitoba Museum, and I'd like to acknowledge that we're on Treaty Number 1 land, which is the ancestral land of the Anishinaabeg, Aninawak, Nahiwawak, and Michif. These lands, waters, and waterways are the unceded territories of the Dakota and the homeland of the Red River Métis. The museum is committed to reflecting the continued legacies of all the original peoples of Manitoba, including the Athiniwak, Denisulanet, I always get that one wrong, sorry, Denisulanet, and Asininu, Inuit, and Nakota. Today, we are going to talk about the universe, which is a pretty vague topic, including as it does everything that has ever been and ever will be that we can ever see or experience or understand. I'm going to try and narrow the focus a little bit, just so that we're not here for an infinite amount of time. For those of you that just maybe saw this particular talk, this is part of a series called Curator Conversations, and all of the curators in the museum are doing talks. Last week was my colleague Joe, our paleontologist, who did a great talk, and other curators will be doing them over the next number of weeks, so you want to come and check those out. I was really honored to be included, since I am not, by any stretch of the imagination, a curator, because well, curator is kind of a museum word. It's, you know, the person who's in charge of the collection of the museum, and they do the research on the collection, and they're really smart, and they know lots of things, and they help create the exhibits that turn into the things that the average person gets to see in the museum. I can't really do that because my collection is not in the building. It is everywhere. Well, I guess technically everything in the building is also part of my collection because I am the curator of the universe and everything in it. So I'm going to show you a little bit of my collection. I brought in our computer that runs the planetarium, and we're just going to make sure that we actually get all of the images that we want here. AV mute off, there we go. So this sort of circular image is being projected on a flat screen, and it is less impressive, but when you see it in the planetarium, it wraps around you, and it is sort of a 3D kind of experience. And this is where we'll begin our tour. That is the Earth. You're familiar with it. It's where you live. It's where you keep all of your stuff. Everybody that you've ever heard of, every piece of history, every great art and poem, every war, everything happened on that little dot. And look at all the other dots. There's a lot of them out there. We're going to take a quick tour here of my collection. Now, this is part of a system which is called Digistar, and Digistar, actually I'm just going to dim the house lights a bit. And I'm just going to go turn off the light that I turned off earlier that someone turned on for me. I'll be right back. Don't want to come all this way and not see. Okay, we've started drifting away from the Earth. Now down at the bottom there's some text there that you probably can't read. It's rattling off numbers in kilometers. That's basically the distance from our planet, the Earth. So I'm just going to pause here. We're about almost 3 million kilometers from Earth in this viewpoint. And you can see our planet there, the little dot, and then there's this sort of oval around it with another dot. That's the moon, and the little oval is the orbit of the moon. And so this is sort of, how many people watched Artemis 2 over the last couple of weeks? It's pretty cool. That's how far they flew. You know, from there to there and around the back and then back there. It looks less impressive when we look at it at this distance, right? This is the thing about the universe, and so my job in curating the universe, is to try and make the incomprehensible comprehensible, because our brains cannot understand infinity. Our brains cannot understand the vast distances or the extremes of temperature and pressure and all of the things that we find throughout the universe. And so my job is to take all of that stuff and present it to the public and try and make it interesting and not terrifying. Because if you think too much about the universe, a little bit of existential dread creeps in, and you start to sort of feel like maybe you're nothing in the universe. I'll get to the end why that isn't the case. But it's a very common reaction when you start confronting yourselves with all of these very, very large distances. Let's continue moving away here. You can see the sun in the upper right, sort of on the right-hand side. That's our sun. Our planet Earth goes around the sun. And all the other dots out there are the stars that we can see at night. There's the Earth's orbit. And it looks a little distorted because, again, this is supposed to project onto a dome, but just go with it. That's the orbit that we take a year to go around the sun. The Earth is, on average, about 150 million kilometers away from the sun, plus or minus a little bit. And there are all the other planets starting to come in there. Now, I'm going to pause again here. We just went out past the orbit of Mars, and then suddenly everything went crazy. This is the asteroid belt. The asteroid belt is a place between Mars and the next planet Jupiter where there's a whole bunch of rubble. How much? Well, there's at least 1.5 million known asteroids. We just have a new estimate in the last few weeks that says there's probably about 6 million. We just haven't found them all yet. Each one of those is a dot representing a particular kind or classification of an asteroid. They're not really rainbow colored, and they're not really that big either. In fact, they're so small that you wouldn't notice them on this scale. In fact, even the Earth, there's the Earth coming around near the bottom there at the end of that blue line there. It's hardly noticeable. Okay, let's continue a little bit farther. And now we're going farther away. We're like, see, 150, we're about 150 million kilometers away. Stop.
No.
There we go. We're about 150 million kilometers away from the sun. And actually, we're just going to move back in a little bit. And you might notice at the bottom, the units changed there. We're not talking in kilometers anymore. It says distance to Earth 3 astronomical units. The numbers just start getting so big that astronomers decided, well, kilometers make me think about millions and billions and trillions and stuff like that. Forget that. Let's just make up a new unit. And it's called the astronomical unit. And the Earth is 1 astronomical unit from the sun. I can handle the number 1. I can handle the number 2, right? So we take all the infinity and immensity and incomprehensibleness of the universe and we hide it in the unit. And then we fool ourselves into pretending that we know what we're talking about. When in fact, all we're really doing is sort of shielding ourselves from that immensity. And this happens throughout history as we learned that the universe was bigger and bigger. This happens a few times. We'll go out a little bit farther here. Now you can start to see the asteroid belt actually is kind of a little bit of a belt. There's the orbit of Jupiter, that white circle there. Saturn's orbit is the yellow one, and then Uranus and Neptune, the ice giant planets, are out there. Now we're about 20 astronomical units away, so 20 times 150 million kilometers. You can do the math if you want, or you can ignore it. And we're also starting to see beyond Neptune more little white dots. It turns out that past Neptune, there's a second asteroid belt. We call it the Kuiper belt, after the fellow who sort of theorized it was there even before we knew anything about it, Gerard Kuiper. And that's where Pluto lives. Pluto is a member of the Kuiper belt. It's a small icy world. We discovered Pluto in 1930, and we didn't know what we were talking about then, really, so we called it a planet. And then we discovered, in the last 20 years or so, we discovered Pluto wasn't by itself. We've discovered 4 other Plutinos, or Plutos, that are almost the same size. We've discovered dozens of smaller objects out in the Kuiper belt. So we realize now that Pluto is kind of like the biggest asteroid in the asteroid belt. It's not really a major planet like Earth or Saturn or Jupiter, but it's something. So the category dwarf planet was invented, and so we called Pluto a dwarf planet. The media took that and said, Pluto's no longer a planet, and it turned into a massive brouhaha, and we still have people fighting over whether Pluto is a planet. Well, there's a species of rabbit that is called the dwarf rabbit, and a dwarf rabbit is still a rabbit. So as far as I'm concerned, a dwarf planet is still a planet. Pluto is still a planet. However, We don't include it in the major planet list, and the main reason for that is for the children. How many of you, probably in about grade 6, had to learn the order of the planets out from the sun? Everybody, right? And I learned a rhyme to help me remember, because that's what you do when you're in grade 6, I guess. Let's see, it was, oh geez, do I even remember it? My very excellent mother just served us 9 pizzas. And that rhyme, each letter stood for one of the planets. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. They took Pluto away, that whole rhyme falls apart. You have to come up with something else now, which is fine. The reason we did that is, well, imagine if you memorize that rhyme and then suddenly they discover Eris. Well, you've got to stick an E somewhere into your rhyme without messing up the kids' heads. And then a few years later, they discovered Haumea and Makemake. What do you do with Makemake? Like, how do you fit that in there? So all of the dwarf planets, even though they're still planets, are not on the list that kids have to memorize. So there, I have solved the Pluto conflict. If you disagree with me, you're welcome to disagree with me, but that is kind of where astronomers are settling. We realized the word planet was just way too big. It seemed like it was obvious. Oh, planets are the things that go around the sun. But now we've discovered more than 6,000 other planets out there. None of them would qualify as planets under the definitions we currently use, which is ridiculous. So this is how science works. You have an idea, you try and classify things, you try and figure things out. More observations come in, things change. You could hang on doggedly to your old wrong ideas and be stubborn and just not pay attention to new evidence. There are plenty of people that do that. But if you're a scientist, you have to take that new evidence and change your ideas and change the way you think about our universe. So all those little white dots there, those are the known ones. There's probably 1 trillion objects out there in the Kuiper Belt. So that's a lot of stuff. That's a lot of things that we've covered, and we're still only in our solar system. And our solar system, while it's super important to us, because we live there, is really not all that big a deal. I mean, you can't even see the Earth from this distance. Like this is like standing at the edge of Winnipeg, and you can't even see downtown. Space is big. Okay, let's move a little farther away here. And we'll get a few other things that pop into visibility. These little trails here, these are the spacecraft that we've sent out into space. The yellow ones are the Pioneer spacecraft, and on the other side, which they'll come around in a minute, are the Voyager spacecraft. Those are the most distant objects that humans have sent out into space. And they have kind of left the main part of our solar system. They're way past Neptune's orbit. They're out past the Kuiper Belt. They're out into what we thought was interstellar space, although it's kind of not. And those are the only things that have gone that far. And there's some dates on there of like when they got to different points. Some of the other circles that have been added there are the dwarf planets that are out beyond Neptune. And then beyond that, there's the Kuiper Belt. As we start to zoom away even more, one of my favorite parts of the thing comes in here. Those are again more trans-Neptunian objects, we call them now, because there's all sorts of different kind, and the only thing that's similar about them is that they are in fact past Neptune. Now as we continue to go away, we're like 500 astronomical units away. We're 500 times farther from the sun than the Earth is. This is one of the most distant objects known that we know that still goes around the sun. Okay, here we are at a distance of, let's see when it stops, 3,226 astronomical units. So 3,226 times 150 million, yada yada. We're out into another swarm of objects. And this is called the Oort cloud. It's another, not just a belt, but actually a sphere of objects that goes around the sun and is the source of most of the comets, like Comet Halley or any of the comets that we've seen recently that were nice and bright. There's a handful of them every year that fall in towards the inner solar system. But they come from so far away that often they will never return in the lifetime of the solar system. And if that isn't enough, let's zoom away a little bit more here.
Yeah.
I'm using the mouse left-handed, and that's my big problem here. There we go. So now we're heading away, we're like 25,000 astronomical units, 30,000 astronomical units. Finally, we're starting to see that the Oort cloud is starting to be all behind us. It's like we can see it as a cloud around the solar system. And then suddenly the units change again. We get to something called 1 light year. Now, that sounds like a calendar thing, some kind of weird daylight savings time or something like that. Well, it's actually a measure of distance, because when you get this far out, measuring in kilometers, you have way too many zeros. So again, we take all of those zeros and all that giganticness and we shove it into the unit and we say 1 light year. It turns out that a light year is about 9.5 trillion kilometers. So 9,500,000,000,000,000. I think that was the right number of zeros. That's just too big to think about. It's the distance that a beam of light will travel in 1 year. Now this is cool, not just because it gives us that sense of security by having smaller numbers to deal with, but it also tells us that the light that you're actually seeing right now would have taken 1 year to travel to your eyes. So if you're taking a picture of this, say for example, at a distance of 1 light year, you're not seeing what it looks like right now. You're seeing what it looked like 1 year ago when that light has begun its journey. You're looking back in time 1 year. So astronomers are time travelers. And 1 year, well, that's a big deal to you and me, but it's not really a big deal in the astronomical sense, because stars and planets and things like that live many, 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 many more years than humans do. But as you start to get farther and farther away, it starts to build up. Now I'm going to speed up the motion here, because if I do this at the same speed, we'll actually not get to anything interesting until about 4 o'clock. And we don't have time for that. Okay, so there's the sun. I'm going to turn on a little circle to go around the sun. There it is, that's our sun, and the solar system, and the Oort cloud, and all that kind of stuff. We've turned on, first of all, some red lines that show some of the constellations, and they've already started to distort a little bit. I stopped a little bit too late, but those are the zodiac constellations, and constellations are totally made up. People made them. They're not real. They have nothing to do with actual physicality. The stars in the Big Dipper, they're not all like stuck on the wall at the same distance. Some of them are closer, some of them are farther. And as you fly out into space, the constellations completely change. The green dots are all of the planets that we have discovered beyond our solar system so far. As of this week, it's a little bit over 6,000 other worlds going around in about 4,000 solar systems. So some of them have multiple planets. And we're just starting this. We can just barely detect the easiest to see, the closest, the more extreme planets. You can see sort of in the middle of the screen there, that cross, that's not where there's a lot of planets, that's just where we had a really good telescope pointing and doing all of its work just in that area. So that's what we actually think the density of planets would be across the whole screen if we could survey that entire screen. Maybe 1 trillion planets, perhaps. The great thing about that is that when we look at all these other solar systems that we've discovered, our solar system, which we thought was the prototype, this is the way planets form, this is the way solar systems are made, we are a freak of nature. Our solar system looks nothing at all like any other solar system we have seen yet. Now maybe we just don't have enough data yet. Maybe we're kind of rare, but we don't quite know. That time will tell. When we get more of those green blobs covering more of the sky, we'll know more. But our solar system is really, really unusual. That's super interesting because our solar system is really unusual for another reason. We live here.
This is the only place that we know that we live. And people will always say, oh, well, there's got to be aliens out there because there's all these other planets. Well, yeah, but they're not in solar systems like ours. We don't know what parts of the solar system are important for life to develop. We know a few things. If you don't have a big planet like Jupiter in your solar system, you're probably not going to have life develop. Jupiter prevents a lot of impacts on the other planets because of its big gravity, and impacts, as the dinosaurs learned, are not good for your health or for evolution or anything like that. Having a big moon like we do, our moon is really big compared to the planet, that gives you a lot of tides. Without tides, life doesn't go from the oceans onto land because they don't have that transitory zone where, you know, there's sort of like part water and part land. There's a bunch of things about our solar system and our planet that are really, really unusual. Does that mean I don't believe in aliens? Well, depends on what you mean. I do not believe that there are reptilian aliens disguised as humans running Pizza Huts and you know, tipping over cows and making crop circles and stuff like that. Because we would have figured it out, I'm pretty sure. Humans are not that dense, I don't think. We would have figured that out. However, I bet there's life out there, for sure. I'm 100% sure that we will find alien life of some kind in the next, well, in 2032. That's when I predict that we'll figure that out. I'll tell you why in a little bit. But now don't get too excited. We're not talking green bug-eyed monsters. We're not even talking plants, or like things like that. We might be talking plankton, or algae, or single-cell bugs, the stuff that lives in like a pond water kind of thing. That's the kind of life I think is common out there. We are pretty special when it comes down to it, cosmically speaking. Okay, we're going to zoom away even farther, and this is all, basically this is the 3D model of the sum total of human knowledge of astronomy, and so it pretty much includes everything in the universe that is known, and the things that aren't known, they take an educated guess at and add in as well. So here, for example, that blue sphere, that's called the radiosphere. About 80 years ago, we started broadcasting radio signals, big radars, TV signals, radio signals, now cell phones and all that kind of stuff. And that stuff is going out into space. And look at all those green exoplanets, those worlds we've discovered that are inside that blue sphere. Any of those planets, if they have aliens on them, and those aliens build a radio receiver of any kind, they could listen in, and depending on where they are, they'd be seeing the 1938 Olympics, or maybe I Love Lucy, or maybe MTV from the 80s when everybody had mullets and stuff. That would be their first impression of us. That'd be pretty hilarious. Now, obviously the same thing goes. Any of those planets that have been broadcasting for that length of time, we could detect their signals. We haven't yet. And that's one of the reasons that we think that, complicated life is rare. Now, I run the risk of going off onto a side talk on each of these little elements. Each one is worthy of its own chunk of time, so I'm going to try and avoid that because I have a time limit.
Let's speed things up. Okay, we're zooming past the stars, we're zooming past the nearby stars. Now we're going out into what we call galactic space. This is our Milky Way galaxy, the city that the sun is a member of. About 300 or 400 billion stars with perhaps a trillion planets. It's this big spiral-shaped disk of stars. There's a supermassive black hole in the middle, so my collection includes multiple supermassive black holes, which is awesome. And so here we're at a distance of 100,000 light years. And as we continue to go farther and farther away, we see that out there are other galaxies, each one containing trillions of stars. Now at this scale, we can't, like the sun is completely lost. Even our galaxy starts to get lost as we get out there into the million light year category. But look how much empty space there is between everything. Like galaxies are the big chunks of matter in the solar system. And they're small compared to the amount of space. I mean, it's right there in the name. That's why they call it space. It's mostly empty. The universe is 99.999999% nothing. You are the 0.0000001% of the universe that is not nothing. That's pretty cool. Here we are continuing far away. Now the Milky Way galaxy isn't even visible, and we're only seeing a few of these galaxies as they go by. We're like, 70 million light years away now. We're getting to the point where we really should come up with another unit, and astronomers have. It's called redshift, and it's kind of hard to understand, and it actually doesn't make anything better, so I'm just not going to talk about it. But astronomers often have good ideas, but sometimes they're not great ideas. Here, we have gone so far out, and it's not showing up on this screen, unfortunately, on the projector, but there's just dots on the screen, and it kind of looks like the Oort cloud with just dots everywhere. Each of those dots is a galaxy with billions or trillions of stars in it. We've gone so far away that we're reaching almost the edge of the known universe, and we can travel about 13.8758 billion light years away before we kind of run into the end of what we can see. Now, that's not necessarily the end of the universe. We don't know if the universe has an end, or if it's infinite, or if it's banana-shaped, or whatever, but we do run into this. In all directions, surrounding us, surrounding everything, there is a very, very faint heat signature that is only 3 or 4 degrees above absolute zero, so it's not really a heat signature, but it's in all directions. It's called the cosmic microwave background radiation. It is essentially the edge of the observable universe. We can't see anything beyond that, not because nothing's there, but because whatever is there has not had enough time for light from it to travel to us because it's so incredibly far away. So yeah, this is my collection, and I'm glad that I don't actually keep it in the building, because there are way too many dangers here to deal with. Supermassive black holes and exploding stars and all sorts of nasty things like that. Now let me switch over, back into the galaxy. We fly back out. The constellations are starting to look better again. There's our constellations of the zodiac. There's the Oort cloud, the outer planets, zooming back in. There's the asteroid belt, and there's good old blue Earth with the moon nearby. And we came back just at a perfect time to see the Earth half lit up and half dark. It is round. There's always one. And to be fair, if you don't think that the Earth is actually round, I'm happy to engage with you, although I'd prefer not to do it here, just because it just takes a little bit of explanation. So there's our planet, the Earth. Now we're going to switch over to off of the Digistar system and back to a little bit more conventional images here. So my collection is the cosmos. Cosmos is a Greek word that means order, and the definition from one of the online dictionaries, the universe, regarded as an orderly, harmonious system, opposite of chaos. Yeah, okay, that's fine. Carl Sagan describes it this way: the cosmos is all that is, or was, or ever will be. Our feeblest contemplations of the cosmos stir us. There's a tingling in the spine, a catch in the voice, a faint sensation, as if a distant memory of falling from a height. We know we are approaching the greatest of mysteries. If you liked the Artemis mission and the poets describing the moon and stuff like that, go back and watch some Carl Sagan, because the man was a poet, in addition to being a great scientist. Now that's classical Western science, and it is dominated by Greek and Roman philosophy and by middle-aged white guys like me. However, it's not the only way to look at things. And so one of my heroes, Wilfred Buck, described some of the information that he has from the Cree people. And they have a concept that's the same thing. Misawayaski is a Swampy Cree dialect word that means all that is above and below all over the world. Basically the same concept. This predates the Greeks by probably several thousand years. If you have the opportunity to see our planetarium show, shameless plug, Wilfred Buck's Star Stories, whenever that's running, you should go and see it if you haven't. It is an amazing way of looking at the cosmos that is so much more welcoming and relevant than some of the old classical Greek stories. We'll talk about that in a minute. But everyone in the world has looked at the sky and come up with a word for the unknowable, the everything, the infinite. And it's not a Western kind of thing. This is a picture from the James Webb Space Telescope, soon to be the most important scientific tool ever created. It's well on its way. It will eclipse the Hubble Space Telescope, which previously held that. Every dot in this picture is a galaxy. This is a tiny little area of the sky. If you held up your finger, your pinky finger at arm's length, it's about a quarter the size of your fingernail when held up against the sky. So just a tiny little space, and look at all those galaxies. So we're starting to now get direct images of the little color-coded dots that we had in the Digistar simulation. This is what we think our galaxy looks like, and we showed this a little bit, but I wanted to show the true extent of it. It's actually a beautiful, natural kind of shape, the spiral here, and it's quite thin. It's kind of like a pizza. So, big and round from the top, and it's, very thin if you look at it from the edge. The sun is out about here, kind of in the suburbs, not right downtown, but not right on the sticks either. So we're not too close to that supermassive black hole or the really energetic area near the center of the galaxy. That would be a bad place to have a planet if you have life on it. There are other galaxies out there. This is a galaxy that you can actually see with your unaided eye. It's the most distant thing you can see. It's called the Andromeda Galaxy. And when we do telescope and binocular nights, it's one of our favorite targets because it's 2.5 million light years away. When you look at that live through binoculars, it just looks like a little fuzzy spot. Big deal, a fuzzy spot. But the light from that fuzzy spot has traveled 2.5 million years through space. It has avoided crashing into other stars or planets. It's avoided getting absorbed by clouds or airplanes or birds or things like that. It's made it all the way down through the atmosphere. It has entered your eye and become part of your head. And it's 2.5 million years old. That immediacy is something that astronomy can bring that a lot of it has a lot of emotional impact, I find. Let's see, a few other things that we have in the collection. This is a globular star cluster, probably about 1 million stars, all in a big round ball. Imagine if you lived on a planet going around one of those stars. It would never be night. You would have so many suns so close to you, it would always be daytime. You would not know that there was a universe beyond your own solar system. You'd have 40 or 50 suns bright enough to see, but you'd never see the stars beyond that. Imagine what your worldview would develop as if you didn't know that there was anything beyond your little globular cluster. And now think about what limitations we might have that we don't understand that has limited our worldview of the universe. This is another thing that you can see in the sky, the Orion Nebula. This is a place where stars are born. Like people, stars are born, they live their lives, they get older, they die, they forge the next generation of stars. This is a place where stars are being born right now. We can watch stars being born. You got to watch for a while. It takes a few 100,000 years to actually make a new star, but still, we're watching it as it occurs. Stars also die. This is the place where a star exploded about 1,000 years ago, blew itself to smithereens, and it actually got bright enough that people here on Earth saw an extra star in the sky in the year 1054, and they were like, oh, what's that? and then it faded away, and now when we look there with a telescope, we see the wreckage of that supernova explosion. And stars are not just like little white dots. Stars are not all like the sun and yellow. They're all different shapes, or not shapes, they're all different sizes and different colors. I guess they're kind of different shapes. There are some of them that are kind of oval shaped. And okay, so here's the sun up in the corner here. There are lots of stars smaller than the sun, but there's also lots of stars much, much bigger than the sun. So we're just kind of an average citizen of the galaxy. We're going to just jump past a couple of these because we sort of saw some of those things in the thing already. This is our sun, and if you've ever seen the Northern Lights, has anyone seen the Northern Lights? Excellent. Okay, a few people. Well, so that's the sun reaching out and touching us at 150 million kilometers. I mean, we feel its heat, we see its light, but that's the radiation from the sun hitting the Earth. And it highlights again how important the uniqueness of our planet is. Without the ozone layer and the magnetic field and the things like that that we have, we'd basically be getting microwaved all the time here. Life would not have developed very easily at all, or it would have been very stunted because of we live right next door to this giant nuclear reactor. Luckily, our atmosphere and our magnetic field take all that radiation and they suck it up to the poles, and it just builds up there until that energy makes the air glow in the dark. And that's what the Northern Lights are. So when there's lots of Northern Lights, it means there's lots of stuff coming from the sun, lots of activity there. That's something that the Inuit were able to understand without the same level of, say, mathematics or scientific understanding, but they were able to use, the Northern Lights to sort of forecast what long-term weather would be, which I think is really amazing. And there was no explanation for it until we understood the Northern Lights and how they were caused, and then it was something, oh, now I get it. Planets, dwarf planets. This is a scale drawing of the solar system. Not the right distance, obviously, we're not all lined up next to the sun, but this is why it's called the solar system. That's the sun on the left. It's the big thing. Earth is the third dot out there. Even Jupiter is not all that impressive compared to the sun. So planets are really small. That's why it's hard to see them around other stars. And then we finally come back to our planet, the Earth. Now, some of you will recognize this picture. This was, you can see the window frame of the Artemis spacecraft on the left there. This was the first picture that we got back from Artemis when they just left the Earth and they were heading off towards the moon. And we got this picture, and everybody was floored. And all of a sudden, social media became 9 days of moon joy and nothing else. And it was wonderful. Look at all the stuff. There's the brown of I think that's Australia there. There's the white of the clouds. There's some ice down on one side. You've got the northern lights and the southern lights sticking out about the edge of the thing. This is actually the dark side of the Earth. You can see the bright edge of the Earth on the bottom right there. That's actually, the sun is coming from the other side, and this is all the dark side of the Earth. In fact, if you download the original image, you can kind of see, oh yeah, on the bottom left there, you can see cities from all of their lights. So all the lights are on. Well, why is the Earth all lit up? Because it was full moon, and the full moon was shining from behind the spacecraft like a spotlight and lighting up the Earth. I love this picture. This is going to go on my wall as a poster, I think. The problem is, of course, there's so many other pictures that came out of that mission. I mean, we watched the launch. There's Jeremy Hansen on the right, and his 3 NASA crewmates. Usually, astronauts are like pretty competent, inspiring people, but I didn't know they were going to send artists and poets up there, because listening to them look out the window and getting excited about the stuff they saw was just mind-blowing. This is another one of my favorite pictures from the mission. This was the first picture this is Earth set, because they were just going around the far side of the moon and the Earth was going to disappear behind there. This was the first one that came back, and I looked at it for I don't know how long without being able to speak. I mean, look, that's us. And then right next door, the moon, look how desolate it is. There's no air, there's no water, there's no magnetic field to protect you from the sun's radiation. There's none of the things that we would need to survive. And yet, it's right next door. The Earth is a special, special place. Okay, and then for me, the big thing of the Artemis mission was they named a couple of craters, and they named one after the spacecraft integrity, and then they named one after Carol, who was Reed Wiseman's late wife, who passed away a few years ago. And I used to say that the Artemis mission was the only bit of the news that didn't make me want to cry. But then it became not true, because this made me want to cry too, just for different reasons. It really was amazing to see how excited people got about this kind of exploration. And I think it's because humans explore. We like that kind of stuff. We learn things, and we like learning things. And sometimes we forget about that, and we get focused on he said, she said, or social media, or all the bad news, or things like that. But look what we can do when we work together. And that was the message of the crew. I mean, this wasn't one country doing this. Canada was involved. The European Union was involved. There were a lot of people working together to make this whole thing happen. And it was pretty spectacular. One of my colleagues came to me last week, and they're like, what am I supposed to do with my life now that there's no live feed from Artemis? Well, now that they're back, they're doing the chat shows. And so there's a 20-minute interview with Ian Hannamansing on CBC that's out, and there's a whole bunch of other stuff where they get into, they've processed their thing a little bit. So there's a whole nother second round of Artemis stuff that you can start to watch, which I'm pretty excited about. Now, how are we for time here? I want to make sure we're not going to... There we go, okay. Yeah, I want to, before we go for questions, I just wanted to sort of, again, connect myself to why I'm here in a series called Curator Conversations. Museums and planetariums grew up very differently. Museums grew up, humans have collected stuff forever. And, sometimes you might see the old curiosity cabinets or things like that. And museums have, of course, evolved way beyond that to, exhibits and using technology and interactives and things like that, engaging all different ages and all different socioeconomic backgrounds. Museums are for everybody. They're kind of like libraries in a way. They had that one purpose to begin with, to have stuff, but they've grown so much beyond that. And so the museum has sort of had several hundred years, I guess, really, to sort of evolve into its current role. The planetarium's been around for 100 years. This is the first planetarium projector. It was made in 1925 by the Carl Zeiss Company in Germany. And it is essentially the same functionality as Marvin in our planetarium. There's a big light bulb in the end of that ball, and a whole bunch of holes drilled, one for every star. And there are lenses for a few other things. And then there's some clockwork in there to be able to handle, like, the moon, which moves around and stuff like that. There's Marvin. This is a pre-drone shot. We actually had our photographer in a harness pulled up to the top of the dome to be able to take this picture for, some kind of conference. But there's Marvin. He's still there. And makes a great job of showing the sky, the stars. The problem is Marvin can't show you anything that the ancient Greeks didn't know about. He can't show you what it's like to be on the moon. He can't take you to a supermassive black hole, things like that. So planetariums have always had extra kinds of projectors, and so now we have a system called Digistar, which I showed you before, that can cover the entire sky, and it's a 3D model of the universe. But the planetarium went through a number of phases. 1925, invented. Then it kind of languished a little bit until the 60s, and suddenly, we're going to the moon. There's the space race, the Cold War. All of our kids are going to grow up to learn to live and work in space. We're going to get we're all going to take rockets to work and have flying cars and stuff. So here's, for the younger viewers, the Cold War was the United States versus the Soviet Union with different countries allied, and then all the unaligned countries there, the gray ones, didn't know which side to pick. And so rather than fighting it out militarily, the superpowers chose space as a surrogate war, a Cold War. And that way they could show their superiority in manufacturing, and if I can build a big rocket to go to the moon, well, I can probably drop a nuclear bomb on your house, so you better watch out. And there was a lot of that sort of posturing and things like that, and that's what took us to the moon the first time. And the Americans won that particular race. The Soviets lost the race, then pretended that they weren't in the race to begin with, and started building space stations, and did a whole bunch of other things in space. And then eventually we've come to the International Space Station, where those two former competitors were going against each other. Unfortunately, never got the flying cars. That promise of technology, again, sort of just disappeared, and those kids didn't grow up to have to go into space. But during the 60s, planetariums were built all over the world. Our planetarium opened in 1968 as a centennial project. So did all the other planetariums in Canada. There were like 8 of them at the time. I worked in Massachusetts for a couple of years while I was waiting for a job to open up here. Massachusetts, the state of Massachusetts, the Commonwealth of Massachusetts, had 31 planetariums. Some of them were just colleges. There were a couple public ones. Some high schools had their own planetarium because they were so sure that they were all going to be living and working in space. We have to get ready for the new space economy. Yeah, that didn't pay off. But these planetariums have now found their educational value, because you can't really teach people stuff. No one can teach anybody stuff. All you can do is inspire someone to want to learn something. And the planetarium venue and the subject of astronomy has that connection, has that ability to reach into people. We saw that with the Artemis mission, where a bunch of people who weren't interested in space suddenly were learning about space. And if you learn about space and science and things like that, you have a harder time maybe falling for some of the conspiracy theories that aren't science-based, or some of the things that are out there that are maliciously trying to, provide you with misinformation. So I feel like what we do in the planetarium, it's very different from what the museum does in its details, but it's exactly the same as what we do at our core, which is to try and inspire Manitobans to take notice of their universe and the place that they live and the things around them, find their connections with the past, the present, and the future, and to enjoy learning, because that's really what it's all about. And build me a flying car. Thank you.